I'd like to welcome our speaker, Robert Wills. He's an engineer at Cisco in Harpenden, and he writes software for internet routers. He has a keen interest in the history of computing and users and what they actually did with the computers, and has been fascinated by the Apollo guidance computer for the last 10 years and is still learning things about it. Today he's going to tell us about the final stages of the lunar descent, which was 50 years ago in July, and the 3 nail-biting seconds in which it appeared that the mission would have to be aborted. So without further ado, Robert Wills.
July the 20th, 1969. Neil Armstrong and Buzz Aldrin were in the lunar lander 30,000 feet above the surface and descending rapidly. All seemed to be going well when suddenly the onboard computer indicated a 12:02 program alarm and the computer restarted. Neil Armstrong, as ever, remained cool, calm and collected and radioed Houston with just a hint of urgency in his voice, asking for an update on that 12:02 alarm. 3 seconds later, Houston came back and gave Armstrong the go to continue. Shortly after, another program alarm occurred, this time at 12:01, and another, and another, and another. In total, during the Apollo 11 descent, there were 5 program alarms and restarts, the last one just 2,000 feet above the moon's surface. There could not be a worse time in the flight to have computer problems. Now, at the time, the press gleefully reported how Armstrong seized manual control from a crippled and failing onboard computer and managed to heroically and single-handedly land the spaceship on the surface of the moon against all odds. Nothing could be further from the truth. Yes, Neil Armstrong was an outstanding and brilliant pilot, but the Apollo guidance computer worked flawlessly in this mission and every other mission that it flew. This was thanks to pioneering hardware and software design principles which were used to make the system robust against any failure, no matter what happened. And those design principles, although pretty revolutionary at the time, now form the basis of all sorts of highly reliable software that we use every day. So in this presentation, I'd like to use the story of Apollo 11 to tell you a bit about the Apollo guidance computer. So I'll start by actually introducing the computer to you, and then I'll walk you through in detail how you land on the moon, and I'll show you the computer and the role that it played in doing the landing. Next, I'll talk about some of those revolutionary design principles that we use to make the software robust. And then finally, once we've got all that background, I'll go back over the Apollo 11 landing and we'll get to the bottom of those program alarms. And I will show you that the Apollo guidance computer saved the mission rather than ruining it. First, though, a little bit about me. So as was said in the introduction, I've been working at Cisco for the last 10 years in the service provider business unit. So we write software for really top-of-the-range routers that you wouldn't normally see. These things sit in the core of like a data center or a whole country's network. And so it's really important that these routers are very reliable. And so there's a lot of links between the things that I do as part of my job and some of the topics that I'm going to be talking about today. In my spare time, I absolutely love the history of computing, and I believe that old computers should not sit on a shelf and gather dust, but they should be plugged in, switched on, brought to life, and demonstrated in the context with which they were designed to be used. Or, if you don't have an Apollo guidance computer and a spaceship handy, at least try and demonstrate it on the screen. And I spent 10 years researching the Apollo guidance computer. It's my favourite for all sorts of reasons, not least the story I'm going to tell you today. Okay, so first let me introduce you to this amazing machine. So there it is on the screen, and it was designed at the MIT Instrumentation Laboratory. It was actually the first contract that NASA awarded as part of the Apollo program. So just 6 weeks into the Apollo program starting, NASA awarded this contract and they realised that some sort of onboard computer would be needed. And it was responsible for almost all of the guidance, navigation and control of the Apollo missions. So it got you into orbit around the Earth, it got you to the moon, it got you into orbit around the moon, it got you down onto the surface, it got you back off again, it managed to rendezvous the two ships back together, it got the whole caboodle back to Earth, and it managed re-entry. The same hardware, but running different software, was used in both the command module, so that's the mothership, and the lunar module, that's the thing that landed on the moon. It weighed only 32 kilograms. This is really important because you pay for the weight 3 times. You pay to get it off the Earth, you pay to land it on the moon, and you pay to get it off again. It consumed only 55 watts. And every time I give this presentation, I double check that number because I just don't believe it. And it occupied only 1 cubic foot. Now, in an era where most computers occupied entire rooms, consumed vast amounts of power, and required huge amounts of cooling, I think those 3 numbers are truly remarkable. And it ran at between 50 and 100,000 instructions per second. This is where the claim comes from that there's more power in your pocket calculator than the Apollo guidance computer. That, as you will see, is a load of rubbish. So getting a little bit more techie now, it was built completely from scratch from one type of logic gate, the 3-input NOR gate. So this is the simplest possible logic gate you could ever think of. And they were able to connect about 5,500 of these logic gates together, and it turns out that you can connect them together to make any digital circuit you can think of. Now, it was actually built from integrated circuits, and so you had 2 of those logic gates on each integrated circuit, and so the computer was made up of just under 3,000 integrated circuits. Now, the choice to use integrated circuits was itself really ahead of its time. For example, in 1963, 60% of the United States' entire integrated circuit production went to MIT for the Apollo guidance computer. So that's how radical it was that they were using integrated circuits. Did they solder them together? Oh no, they welded them together to form these modules. And then 26 modules plugged in to a backplane, and the backplane connected all the modules together and made the final computer. There's a slightly bigger picture of the tray with some modules plugged into it. And there's a picture of the other side, that's the backplane. Those blue lines you can see are little wires that are connecting all the modules together. In terms of memory, there was a really, really tiny amount of memory in the computer. So there were 2,000 words of erasable memory, what we would call RAM, and that's where variables would be stored. So in English, that means you can store 2,000 different numbers in your computer. For example, you might store where you are, you might store where you're going to be landing, you might store various other bits of information like your speed. So you can store just 2,000 of those numbers, which, believe me, is not very much. And it had 36,000 words of fixed memory, what we would call ROM, and that's where the program was stored. And so, more in English again, that means you can store 36,000 instructions in your computer. So really not very much of either of those things. Now, the fixed memory is pretty cool. So it's actually here on the slide, and you can see there's these very thin copper wires. This is all magnified. These very thin copper wires going through these rings. And roughly speaking, if a wire went through a ring, that was a 1, and if it didn't, that was a 0. And so the software was literally woven together to form the fixed memory. There's a picture of an engineer at Raytheon She effectively has the program listing in front of her, and she is very carefully weaving those tiny copper wires through the even tinier rings to translate the program into the fixed memory that the computer can then read. You wouldn't want to make a mistake there, would you? Now, given it was made up of only 5.5 logic gates, it was surprisingly featureful. It had a real-time clock, interrupts, parity checking, and extensive input and output connectivity. But it also had some quirks. It had a 15-bit word size. What that means is the numbers it can store are not very big. It used ones complement for integers, which will shock any mathematician because you can have two different values for 0, positive 0 and minus 0. And believe me, this is not used in any computer system today for obvious reasons. It had no floating point numbers, so you couldn't have anything with a decimal point. Everything had to be a whole number. But actually, it turns out that's not too bad. You can work with that, and in many ways, that's preferable. And instead of having lots of different instructions, it did quite a lot with these weird memory locations. So for example, rather than a special instruction to shift a number one place to the left, which turns out to be a really useful thing to be able to do in a computer, rather than a special instruction to do that, you would write your number into the special location 20, and then magically, when you read it back again, you get the number shifted one place to the left. So that was kind of another quirk of the instructions. As we've seen, it had a very tiny amount of memory, it had no stack, and a bizarre and awkward instruction set. If you gave a modern-day systems engineer the Apollo guidance computer's instructions, they would be really scratching their heads to try and figure out how to use those instructions to make a program. Okay, let's talk about I/O. So this thing on the screen called the DSKY was the main way that the astronauts interacted with the guidance computer. And you can see it's got a display on the top right that can show you some numbers. It's got a keypad at the bottom for entering some data, and on the top left you can just about see it's got some special lights. The DSKY used a verb-noun format for entering commands and displaying data, and there are many other human interface devices present in the spaceship, for example the 8-ball, indicator lamps and hand controllers, and I will show you all of this later on. The computer could also radio data back to Houston and receive data from Houston. And of course, a spaceship has lots of very exciting I/O. For example, a rocket engine is I/O. The computer is able to control the rocket engine. It's also able to read data from lots of specialized instruments, which again I'll talk about later. So one of the things that the guidance computer was really good at, because it had to be, was input and output. Okay, so that's the computer. Now I'd like to talk to you a bit about how they landed on the moon with Apollo. First of all, we're going to need a spaceship. So here's our spaceship. And the first thing that we need is a big rocket engine. And that rocket engine will give us lots of thrust, and we'll use that thrust to slow ourselves down. That will take us out of orbit and gently onto the surface. So there's our big rocket engine. However, we also need to be able to steer, and that's the job of these little RCS thrusters. The RCS thrusters allow the computer to steer the spacecraft in any direction. The main source of data is this thing called the IMU. The IMU can tell you which way the spacecraft is pointing, and it can tell you which way the spacecraft is accelerating. And with those bits of information, you can calculate the position and the speed. There's also the landing radar, which uses radar to measure the height of the spaceship above the moon's surface. There's the window. The window is very important. I'll have a lot to say about that later. On the feet of the spacecraft are these little probes called the lunar contact probes. And in the middle, tying everything together, sits our best friend, the Apollo guidance computer. So that's our spaceship. I'll just talk very quickly about a couple of things that will be less familiar to you. First, the RCS thrusters. So on 4 corners of the spacecraft are these quads of RCS thrusters, one pointing up, one pointing down, and two pointing out at right angles. And the computer can give little squirts of thrust through these tiny thrusters, and using those little squirts, it can steer the spacecraft in any direction the computer wants to. The other thing worth talking about quickly is the IMU. The IMU was a remarkable piece of engineering. It was a sphere, and inside the sphere were three concentric rings which could rotate around each other. And then right in the middle of the IMU was something called the stable member. The stable member had three gyroscopes on it, mounted at right angles to each other. And because they were gyroscopes, that keeps the stable member completely fixed in space. So the spacecraft can move around however it likes, and the stable member stays completely in the same place. Now, there are sensors on the concentric rings, and you can use those sensors to see how the spacecraft has turned around the stable member, which is always fixed. And so by taking those measurements, you can measure which way the spacecraft is pointing. And there are also three accelerometers, a bit like in your phone, that can measure the acceleration in three directions. Okay, so that's enough about the spaceship. That's all you need to know about that. Next, I need to give you a 2-minute course. I need to condense hundreds of hours of NASA training into 2 minutes and tell you how they landed on the moon. So let me set the scene for you. We're coming into the mission at the point where the astronauts are in what was called the descent orbit. Now, this is a really misleading name because the descent orbit doesn't actually take you down to the surface of the moon. The descent orbit is an ellipse, and the lowest point of the descent orbit is 9 nautical miles above the surface. And the lunar module could quite happily go round and round that descent orbit forever and ever. In order to land on the moon, we need to execute a series of maneuvers starting from that lowest point in the orbit, and those maneuvers will take us out of orbit and gently down onto the surface. Those maneuvers are the hardest bit of the landing, and that's the thing I'm going to be talking about today. Now, that comes in 3 phases. The first is P63, the braking phase. Now, the aim of P63 is to slow the spacecraft down. And as the spacecraft slows down, it will also lose lots of height. So the spacecraft starts 9 nautical miles, or 50,000 feet above the surface, and it's going really fast, 1,670 meters per second. During P63, we fire that massive rocket engine. That slows us down. We lose most of our height. So at the end of P63, we're much lower. We're only 8,000 feet above the surface, and we're going much slower, 210 meters per second. So that's P63. Next is P64, the approach phase. Now, up until this point, the astronauts, broadly speaking, are on their backs with the rocket engine pointing out in front of them, and they can't really see where they're going. So the first thing that happens at the start of P64 is that pitch-over maneuver, and that allows the astronauts to see forward out of the window to see where they're going to be landing, which is kind of useful. During P64, the astronauts and the computer work together to fine-tune the landing site. Finally, when the lunar module is about 200 feet off the ground and it's basically above the landing site, we enter P66, the final phase. The aim of P66 is to touch down nice and gently, vertically, and without any side-to-side or forwards or backwards movement. So that's the 3 landing phases. P63, the braking phase, where we slow down and lose most of our height. P64, the approach phase, where the astronauts and the computer work together to fine-tune the landing site. And P66, the final phase, where we want to touch down in a nice and gentle manner. Okay, so that's how they did it. Now I'd like to rewind the clock and show you the computer in action doing its stuff. Now, there's quite a lot of detail here, and you don't need to remember any of the detail to enjoy the rest of the talk. I just want to sort of demonstrate to you the sort of things that the astronauts and the computer were doing, so you get a flavour for what's happening. Okay, so let's rewind the clock. We're back in the descent orbit, and we're about 10 minutes before we're due to start the landing manoeuvre. And the astronauts have the disky in front of them. Remember, that's the main way that they interact with the computer. And the first thing they need to do is load the landing software. So to do that, they type in verb 37, which means please load this program. And then they type in the program number. So program 63. They press enter. And the computer loads the landing software. Now, the computer has been programmed ahead of time with where the landing site should be. And the computer calculates at exactly what time it needs to start firing the rocket engine to start that landing manoeuvre. So the computer displays that to the astronauts using verb 6, noun 61, which means I have some information about the landing to show you. And the most interesting number, if you're excited about getting to the surface, is the second one, the time until ignition. So here it's saying it's 600 seconds before the computer's calculated that we need to light the engine. Okay, so fast forward, we're now 100 seconds before ignition, and the computer has an important message. So to signal that to the astronauts, it illuminates the key release light on the disky. The astronauts can view that message by pressing the key release button, and the message is verb 50, noun 18. Well, what does that mean? Well, that is the computer asking permission to manoeuvre the spacecraft. Now, if you remember, at the start of P63, we need the spacecraft sort of on its back with the rocket engine pointing out in front of it. And so the computer is asking permission to do that. If the astronauts are happy, they press the proceed key, and then the computer automatically manoeuvres the spacecraft so it's pointing the right way. The next thing the computer does is called ullage, and it fires a little jolt through some of the RCS thrusters. And that jolt settles the rocket fuel in the bottom of the fuel tanks so that the rocket engine will ignite cleanly first time. So they really did think of everything. Now wind forward the clock again, we're now 5 seconds before ignition. And the computer flashes verb 99, noun 62. Now every Apollo astronaut can tell you what verb 99, noun 62 means. It means, are you sure you want to land on the moon? So the astronauts have 5 seconds to calmly reach over and press the proceed key to authorise the computer to perform the landing. So we're all ready to go. Just to remind you, we're in our descent orbit. We're now at the lowest point, and at exactly the right time, the computer is going to start the landing manoeuvres. So here we go. Well, we know how this works. It starts with P63. And the first thing the computer does is my favourite bit of the whole software. And it made my year when I found out about it. It lights the rocket engine at a very measly 10% thrust, so barely noticeable thrust. And it does that for 30 seconds. Now, what on earth is it doing? Well, the computer is measuring to see whether that thrust causes the spaceship to spin around. And if the spacecraft starts spinning, the computer swivels the rocket engine to make sure that the thrust acts perfectly through the centre of gravity, and that will stop the spinning. So after about 30 seconds of sort of gently firing the engine and gently swivelling the rocket engine, once the computer is happy, it ramps up the thrust. Oh yeah, there's my swivelling. There we are. It's exciting. And there we are. So the computer's ramped up the thrust. And for reasons you can ask me in the Q&A, full thrust is 94%. Now, this is not just a question of fire a massive rocket engine and hope for the best. Throughout the entire landing, the computer is running sophisticated guidance calculations, and it always has 2 points in mind. The first one, in green, is the desired landing site. So that's the landing site that's been programmed into the computer. And that desired landing site can actually move, as I'll show you later. The other one is the projected landing site in blue. And that's where the computer thinks it's going to land based on its current position, its current speed, and doing some orbital mechanics to extrapolate the trajectory. And the computer's whole reason for existence is to steer the spacecraft to try and move that projected landing site towards the desired landing site. So, sophisticated stuff. Okay, again, don't worry about the details, just enjoy the computer doing its amazing things. At the start of P63, the landing radar is too high above the surface to be able to see the surface. So the only source of data the computer has is from the IMU. Now, the IMU is extremely accurate, but it loses accuracy during accelerated flight. And of course, nothing says accelerated flight like having a massive rocket engine lit up your backside. So the computer signals to the astronauts that it doesn't know exactly where it is or exactly how fast it's going by illuminating the altitude and velocity lights on the disky. Okay, we're still in P63, but we're now a bit lower. We're 40,000 feet above the moon. At which point we're low enough that the landing radar can lock onto the surface and start providing data to the guidance computer. So when that happens, the computer clears those two lights, and the astronauts are eagerly waiting for this moment. When it happens, they type in verb 6, noun 63, which means, please show me the discrepancy between how high you thought you were, based on the inaccurate data from the IMU, and how high you actually are, based on the very accurate measurement from the landing radar. And it was common, 40,000 feet above the surface, for there to be a 1,000 feet discrepancy between where the computer thought it was and where it actually is. Now, obviously, when you're 40,000 feet above the moon, 1,000 feet here or there doesn't make much of a difference. But as you start getting lower, you really want to start using the more accurate numbers. So the astronauts kind of check this data, they sort of make sure it looks vaguely okay, and if they're happy, they do something called incorporating. To incorporate, they type in verb 57, which means, you guessed it, please incorporate, and the guidance computer will then merge the very accurate height information from the landing radar with the information it already has from the IMU to get a much more accurate position. And then over time, the guidance computer will steer the spacecraft to correct for any discrepancy now that it knows exactly where it is. Okay, so we're more than halfway through the landing now. Towards the end of P63, the computer automatically ramps down the thrust at a precisely calculated time to keep the spacecraft on the trajectory. And then when it reaches 8,000 feet, it automatically enters program 64. That's the next bit of the landing. Well, we know what happens from our 2 minutes NASA training. The first thing the computer does is it does that pitch over maneuver to get the spacecraft sort of more vertical. Now, if you remember, during P64, the astronauts and the computer work together to fine-tune the landing site. So the computer needs some way of telling the astronauts exactly where it's going to land. It needs a very sophisticated device. Yes, it's the window. The window has these two axes marked on it, like that, a bit like graph paper in school. And during program 64, the computer shows verb 6, noun 64. And that means I'm telling you where you're going to land. And it works like this. You see that 5 on the top row of the disky? That tells Armstrong to look 5 along the horizontal axis in the window. And that 40 on the right-hand side tells Armstrong to look 40 up the vertical axis. And so Armstrong then imagines a red dot looking out the window, and that red dot is the computer telling Armstrong exactly where the spacecraft is going to land. So throughout this part of the landing, Buzz will be calling out the numbers like 5, 40, and Armstrong will be looking out the window using those axes to imagine the red dot, and he can see, oh, that's where we're going to land. Okay, what happens if Armstrong doesn't like the look of where the computer's going to land? Well, he can move his hand controller. And if he moves his hand controller, that moves the desired landing site. And then the guidance algorithms will steer the spacecraft to move the projected landing site towards the new desired landing site. And it was common throughout P64 for that imaginary red dot to move around the window, especially if Armstrong was using his hand controller to change the landing site. So Buzz might be saying 5, 45, 5, 40, 5, 0, etc. And Armstrong all the time is using his hand controller to fine-tune the landing site if he wants to. Throughout Program 64, the hand controller is connected to these very sophisticated guidance algorithms because the hand controller doesn't directly steer the spaceship, it moves the desired landing site. And then the guidance algorithms will calculate how the spacecraft should be steered to achieve that. And then those steering commands go down to the much lower level attitude control software, which takes those steering commands and turns those into commands that get given to the thrusters. So there's a lot of sophisticated code between the hand controller and the thrusters. Once the lunar module is pretty much above the landing site, Armstrong moves that pings mode switch from auto to attitude hold. And roughly speaking, that automatically puts the computer into Program 66. At which point, the hand controller is disconnected from the sophisticated guidance algorithms and instead is plugged directly into the steering software. So that means that when he moves his hand controller, rather than changing the landing site, he's directly steering the spacecraft. So it's a much more direct relationship of control in the final stages of the landing. But the point I want to make is that it's not total manual control. At all times, there is code running in between Armstrong's hand controller and the thrusters. Finally, once the lunar module is really close to the ground, lots of dust gets kicked up and Armstrong can no longer see out the window. So he looks at two instruments inside the cockpit, both controlled by the guidance computer. The first is the 8-ball, and that tells him, is the spacecraft the right way up? And the other one is the cross-pointer display, which tells him, is there any side-to-side or forwards and backwards speed? And Armstrong looks at these two instruments to make sure that the spacecraft is completely vertical and isn't sort of shifting side-to-side or forwards or backwards. And this is very similar to how a pilot would land an aircraft in the fog. Finally, you remember those little probes on the feet of the spacecraft? Well, once they touch the ground, a blue contact light illuminates in the cockpit. The astronauts quickly switch off the engine, breathe a sigh of relief, and that's how you land on the moon. And that's my demonstration of the Apollo guidance computer. However, what about those pesky program alarms? Well, in modern that's a serious problem. That's a bit like seeing that on your computer. Or if you're a little bit more old school, something like that. Or, worst of all, that. The 1202 alarm was nothing to laugh about if you were in the spaceship itself. Now, of course, they always had the option of aborting, but an abort was by no means a trivial thing. Obviously, you lose billions of dollars that have been spent on or at least hundreds of millions, on the mission. You lose a huge amount of national pride and your own pride. But aside from all of that, it's actually technically very difficult to abort. So if they pushed the abort button, 4 pyrotechnic bolts would have exploded, They would have separated the lunar module into two, so the whole descent stage would have come away, just leaving the ascent stage. A fifth pyrotechnic would have fired, which would have fired a guillotine across all of the cables connecting the two stages together, so completely separating the spacecraft in two. So you can only abort once, if you know what I mean. You can't have another go. And then, of course, Mike Collins in the command module has a very big orbital mechanics problem to solve because he has to go and pick up his friends. So an abort was a completely non-trivial and not safe thing to do. So the question of what we do about the 1202 alarm was a very serious one. And so that's what I'd like to talk about in the latter half of the presentation. So first, I want to talk a bit about the mission software, and then we'll leap back into the cockpit and get to the bottom of those program alarms. First, though, a little bit about the software. Now, this is a slightly a drier 10 minutes of the talk, but just bear with me. Let me say what I've got to say, and then we'll jump back into the spaceship and have fun for the last 15 minutes. The software in the lunar module was called Luminary. And I hope in my demo I've persuaded you it was a sophisticated piece of kit. It controlled all phases of the mission, so it got the lunar module into that elliptical descent orbit. It managed all of the landing, that's the stuff I've just been talking about. It got you off the moon again, and it got you rendezvoused back with the command module. So it did everything. And as we've seen, it controlled that massive rocket engine, it fired the RCS thrusters, it was updating information on the disky, it was moving the 8-ball and the cross-pointer display, reading data from the IMU and the landing radar, doing all sorts of things, all at the same time. So it ran a very simple real-time operating system that they wrote from scratch as part of Luminary. And I want to very quickly talk about 6 design principles that they used in that real-time operating system to make it reliable. Oh, I always forget this bit. The source for Luminary is available on GitHub. Yes, very good. Okay, number 1, use a high-level language. So as I said towards the start, the Apollo guidance computer's instructions were very primitive and difficult to use. And that meant that you had these complicated guidance algorithms, and it was difficult to translate those into code that was correct. Also, the 15-bit integers, the small numbers that the computer can store, were not big enough to give the kind of accurate precision that the guidance computer needed. So their solution to this was something called the interpreter. This provided a sort of virtual set of instructions that were much more powerful. So for example, they gave you matrix and vector operations, which are really useful if you're doing guidance calculations. They gave you such luxuries as being able to index into an array. And they gave you a stack, which is good for writing much more structured, readable code. It got round the 15-bit word size by giving you double and triple precision integers, so it gave you much bigger numbers to work with. And that gave you the accuracy that you really needed for those calculations, working out the landing site and how you should steer the spacecraft, etc. It also meant that the same algorithm took up a lot less space because each instruction did a lot more things for you, so you needed fewer of them to get the job done. And if you remember, there wasn't very much memory, so if your program took up less space, that was a really good thing. It also made it easier to write correct code because the instructions were easier to use. But the downside of the interpreter was it ran really slowly. So the final software was a blend of both things. The really time-critical stuff, like controlling the thrusters or reading data from the IMU, that had to be done all the time and in a really timely manner, those were written in the difficult-to-use, low-level language. And the interpreter itself had to be written in the difficult-to-use language as well. But then all of the deluxe guidance algorithms that were doing complicated maths were written in the interpreter. And they could do that because those guidance algorithms only had to recalculate stuff every second or every 3 seconds, so it didn't matter if they ran slowly. Number 2, divide your system into jobs. The guidance computer was doing lots of things sort of all at the same time. And so they split the system up into jobs where each job did one thing, a bit like different apps on your phone. So for example, there was a job called redax which read data from the IMU and used that to calculate the position and the speed of the spacecraft. There was a whole suite of jobs used to implement the digital autopilot. There was a charmingly named job called pinball, and pinball updated the numbers on the disky. There were jobs for the high-level tasks like P63, P64, etc., and tens of other jobs that I haven't even included here. If you remember one thing, remember this. Each job had a small area of memory that it could use for sort of temporary storage, a bit like if it was doing some calculations, it had some space where it could sort of show it's working. And there was enough memory to have 7 jobs on the go at any one time. And they very carefully, really carefully, designed the system so you would never have more than 7 jobs running at the same time. Number 3, restart on failure. Now, speaking as a grey-haired software engineer, it is a sad fact of life that all software will encounter failures. Now, I'm not talking about bugs where the programmer misunderstood what the program should do or the programmer was lazy. Those things would be caught much earlier during testing. I'm talking about 1 in a million, once in a blue moon kind of events that are really rare. And those really rare events can trigger unusual code flows through the software that can cause the software to fail if you sort of didn't think about that eventuality. And you often wouldn't find these things during testing because they only happen 1 in a million times. So you'd have to be really lucky during testing to hit the error condition. If your software has failed, it cannot be trusted to recover itself. It's failed, so all bets are off. So instead, you restart the bit of software that's failed. And the hope is that if you restart the software, whatever transient condition was happening that caused it to fail will have gone away, the software can have another go, and hopefully this time it will work, and the system will recover. The guidance computer provided several levels of restart, so you could restart just the failed job, you could restart a group of jobs, you could restart everything but leave vital information like where you are and where you're landing intact. That was called a poodoo. You can ask me about that in the Q&A as well. Or you could literally switch the hardware off and back on again. That was called a fresh start. Okay, we're halfway through, so bear with me on the design principles. Number 4, checkpoint your good state. So restarting is great, but you lose whatever it was that your job was doing. So when your job reaches a sensible point called a checkpoint, it can save that point for later. And then if the job gets restarted, it can read in what it saved and pick up from where it left off. For example, if you're the job that reads loads of data from the IMU and then eventually calculates the position, you'll be doing lots of calculations and then eventually you'll get a result. And so once you have a sensible result, you might checkpoint that so that if your job gets restarted, you can read in the position that you last calculated and pick up from there. You might say, well, what happens if the checkpoint is bad, and in that case, the more draconian restarts like the poodoo and the fresh start would clear out the checkpoint. So jobs would have to sort of do more work to get back up and running, but they would at least be starting from a blank slate. Number 5, hardware monitors the software. And this is the most techie one. The guidance computer, to kind of make it look like lots of things were running at the same time, it used cooperative multitasking. And this is different to most modern software systems. With cooperative multitasking, if you're a job and you're running, then every so often you have to explicitly check to see if there's another job that's waiting to run. And if there is, you have to give up control to the job that's waiting. And in the guidance computer code, the way you did that was your job had to check a special variable called new job. If new job didn't have anything in it, then your job could continue running happily. If new job had a value in it, then you had to immediately give up control to whoever was waiting. And the sort of coding guidelines for Apollo were that a job had to write code to check this new job variable every 20 milliseconds. So there'd be explicit checks sprinkled through the code to check new job. You might say, well, isn't this a bit rubbish? Because you have to add these checks into your code, and it relies on actually people doing the checks in the first place. But bear in mind, this software was all written by one team, everyone was on the same side, and the software has a very specific, well-defined purpose. So in those situations, it's actually simpler to reason about this kind of multitasking, and besides, it was the only feasible way of doing it. Now, you might ask, well, what happens if for some reason a job hangs, so it gets in some infinite loop and never ever checks new job again? Well, in that case, even if lots of jobs are waiting, they'll never get to run because new job never ever gets checked. Well, the solution to this is in the hardware. So the hardware knows about the new job special variable. And so if the software gets stuck and never checks new job again, then the hardware will reset the computer itself after 640 milliseconds. So that's how the system stopped hanging. And finally, number 6, send telemetry. So in the demo, I was showing you the DSKY, and if you remember, it's like verb, noun, and 3 numbers. So that's enough for the astronauts, but it's quite a primitive way of understanding what's going on. Houston needed a lot more information. So the guidance computer would periodically send its internal state back to Earth. And that would be about 100 numbers giving the state of the computer. For example, where it is, how fast it's going, the desired, where it's going to land, the current program that's running, the number of jobs, etc., etc. So loads of information. And then back in Houston, there was an entire team of people completely dedicated to looking after the guidance computer. And they would all day stare at this telemetry to make sure that the system was working properly. So just to sum up, use a high-level language so that complicated algorithms are easy to write. Divide your system into jobs where each job just does one thing. If software fails, restart it. Hopefully, whatever caused it to fail will have gone away and we can have another go. Checkpoint your good state so that if you get restarted, you can pick up from a good place where you left off. Hardware monitors the software to make sure the system doesn't hang. And send telemetry about your system to a group of experts who can understand it and make sure it's working. Okay, so now I'd like to jump back into the cockpit and explain those pesky program alarms. First though, I've lied to you. There was an extra radar on the spaceship called the rendezvous radar. And the rendezvous radar was completely useless when you were landing on the moon, utterly useless. But when you were taking off again, the rendezvous radar is what was used to find the command module. And I should say, in this section, I am making a couple of simplifications, but I'm telling it better than most people do, so you'll still get the better story than most. Now, we've seen there's all this complicated software running that's doing all this landing stuff, and it was actually the most processor-intensive part of the flight. So it put the computer under about an 80% load, which, for any engineer, that's actually quite close to the wire. But that's okay. The problem was the rendezvous radar had a hardware bug that they never found during testing, but well, landing on the moon is a 1 in a million event, and so sure enough, during the real landing, they hit the hardware bug. The hardware bug meant that the rendezvous radar sent a stream of data to the computer. And the stream of data was, I can't see anything, I can't see anything, I can't see anything, I can't see anything. It's a bit like having a really annoying friend tap you on the shoulder, you turn round, and they've got nothing to say. And they keep doing it. This hardware bug puts the computer under a 15%, so it puts an extra 15% load on the computer. Now 80 plus 15 is 95%, even I can do that. So actually, that's fine. There's this hardware bug, but the computer can still stagger on. It's totally fine. And this meant that when they were in the descent orbit, and actually even in the first bits of P63, they didn't notice that anything was wrong, because the computer was just about able to handle the load. So what changed? Well, what changed was Buzz Aldrin. Buzz Aldrin was clearly very excited to be getting down onto the moon. And so he typed in verb 16, noun 68 into the computer. That means, please show me some extra information about the landing, and please constantly recalculate that and update the display. Now, I'm making fun of Buzz here, but this was a perfectly fine thing for him to do, and he'd done it in training hundreds of times without any problem. However, in order to handle that request, an extra bit of code gets started to handle the verb 16, noun 68 task. And that puts the computer under an extra 10% load. So now the computer is overloaded. It's only slightly overloaded, but it is overloaded. And so over a course of a couple of seconds, it falls over in slow motion, like this. The jobs pile up. And the computer, because it's overloaded, can't quite dispatch them quickly enough. And so 7 jobs get scheduled. And when it comes to the 8th job that should never happen, there's a problem. There's no memory to store that job. And that's what the 1202 program alarm means. So what does Buzz see? Well, he's keyed in verb 16, noun 68, and he's studying the disky and rubbing his hands. He's going to have his place in history. And then a couple of seconds later, he sees 2 lights that you never want to see when you're landing on the moon. The first is the program alarm light, followed rapidly by the restart light. Now Buzz needs to diagnose this pretty sharpish. To do that, he types in verb 5, noun 9, which means please show me the program alarms. So the computer says that a 1202 alarm has happened, and that 3 is the restart type. But the system recovers and the spaceship keeps flying. So how did that work? Well, if you remember, that's the situation we got to. There's the extra bit of code running Buzz's 1668 with the extra 10% load. The 1202 happens. The computer restarts various bits to try and recover. But crucially, it doesn't restart the thing that Buzz asked for, because it's considered not important enough. And so that extra load goes away, the computer's no longer overloaded, and the spaceship keeps on flying. So that's the first 1202 alarm. But Buzz, of course, is really annoyed, because he's asked for verb 16, noun 68, and it's gone from the disky. He's just got this pesky program alarm instead. So he reaches over, he types in verb 16, noun 68 again. Sure enough, the same thing happens. This extra bit of code gets started, and it's the same as before. It puts a 10% load on the computer. The system slowly falls over. Once it gets to scheduling the 8th job, a program alarm gets triggered, the very similar 1201 alarm. Once again, the computer restarts bits of the software to desperately try and recover. It doesn't restart the thing that Buzz asked for because it's considered not important enough. The system recovers. So that's the second program alarm. But Buzz, he just can't take the hint. He keys in verb 16, noun 68 again. And that triggers the third alarm in exactly the same way. And there is this brilliant moment in the mission recording where the penny slowly drops and Buzz realizes the connection. And he slightly sheepishly says, "It seems to happen when we have a 1668 come up." Now, From that point, I can assure you that Buzz is sat on his hands. He's not touching the disk key again. He never types in verb 16, noun 68 again, because he correctly realises that for whatever reason, it's causing these issues, even though the spaceship is still flying. Okay, so that's half of the story. But there were 5 program alarms in total. The last 2 happened much later in the mission. So the first 3, I should say, were all more than 25,000 feet up. So, I mean, that's bad that they happened, but when you're 25,000 feet up, you've got plenty of time to diagnose the problem and figure out whether it's safe. The last 2 happened 2,000 feet above the surface, a lot later, during P64. Why did they happen? Well, we know how P64 works. That's the computer calculating the imaginary red dot, Armstrong's moving the hand controller to change the landing site, the computer's doing all sorts of calculations to figure out how the spaceship should be steered. It's naturally just doing more work. And so the load that the software is under naturally increases. And the computer, together with the hardware bug, naturally overloads itself without any intervention from Buzz. So the fact that P64 is more complicated than P63 causes the last 2 program alarms. But there's one final mystery. Why was it that when Armstrong heroically seized manual control, why did the program alarms stop? Well, that's simple. He didn't seize manual control at all. We know what he did. He entered P66 so that he had much more direct steering of the spacecraft. And he actually entered P66 early because he really wasn't happy with where the spaceship was landing. They were quite distracted by the program alarms, and he wanted to rapidly take control of the spaceship and rapidly reposition it. So he entered P66 early. And we know what happens when you enter P66. The hand controller connects to the much lower level code, which naturally reduces the load that the computer is under. So Armstrong, by entering P66, reduces the load. He doesn't know that that's going to happen, but the load reduces, and that's why no more program alarms were seen during the very, very final stages of the landing. So just to go back to those design principles, how did they help? Well, restart on failure. These program alarms happened, bits of the software were restarted, and that allowed the computer to recover. Divide your system into jobs. That meant that even though some bits of the software were being restarted, the really crucial landing software, particularly the software that kept the spaceship stable, always kept running. And it also meant that non-essential things like Buzz's 1668 were not restarted. Checkpoint your good state. So even though some bits of the autopilot was actually restarted, the autopilot was using checkpoint. So the autopilot would start up and it would say, well, what am I supposed to be doing? And it would look at its checkpoint and it would say, oh, we're landing on the moon. Where are we landing? Oh, here, it's in the checkpoint. Where are we? Oh, it's here in the checkpoint. So even though the autopilot was restarted, it could sort of recover roughly from where it was. And finally, send telemetry back to Earth. So I hope I've persuaded you, even diagnosing the program alarm was a real faff. But the fact that the computer was sending lots of information back to Houston gave Houston the authority and the confidence to give Armstrong the go to continue. Because in Houston, with the telemetry, they could see that the flying bit of the software was all still working. So wrapping up, I'd like to pick out 2 people from the 400,000 who worked on the Apollo project. The first is Steve Bales. He accepted the NASA Group Achievement Award on behalf of the entire Apollo 11 mission operations team. This is a much more sort of exciting award than you'd first think from the name. In the words of Nixon, this is the young man when the computers seemed to be confused and when he could have said stop, or he could have said wait, said go. It was Steve Bales who understood the technical meaning of the 12-ritter alarm. It was he who recognised that the spaceship was still flying correctly, and it was he who realised that the system in this exact situation would recover. And finally, Margaret Hamilton, who led the team at MIT, who developed all of this amazing software. And she, finally, received the US Presidential Medal of Freedom in 2016 for her work on Apollo and her entire career developing reliable, robust, fault-tolerant software. And this is the highest civilian award you can get in the United States. And finally, just tying it back to modern day. So these pioneering techniques I've talked about now form the foundation of all sorts of robust software that we use every day, such as the top-of-the-range routers that I work on. For example, there are all sorts of weird things that can happen to these routers. Maybe a particularly weird or bad packet gets sent. Maybe the user enters some unusual configuration. Perhaps the customer wants to hotfix the code without interrupting the flow of traffic. Using all of these techniques on modern software in 2019 isn't quite as cool as Apollo, but it's still really awesome. So thank you very much for listening, and I will take any questions if we have time.
I've seen the graticules on the window in lots of Apollo films, and what I've always wondered is, surely it matters where your head is, and how did they manage that?
So the window was either double or triple glazed, and on two of the panels was a cross, so Armstrong would make sure that he was looking out so that the two crosses merged together. And again, that's common in aircraft cockpits today as well.
The Apollo program started in the early 60s,
yes.
And I'm wondering, this computer system, you focused a lot on the descent, but from Apollo 1 to Apollo 10, where they were just attempting to travel to the moon but not land, at what stage was this computer system developed, and what part did it play, if any, in Apollo 1 to 10?
I don't have a precise answer to that. So the one thing the computer didn't do was getting you off the Earth. There was a separate computer in the Saturn V rocket that did that. So the kind of very early stuff of let's just get off the Earth, they didn't need this computer for. There were two sort of major iterations of this computer, Block 1 and Block 2. Block 2 was the computer that got you to the moon. Block 1 was a more primitive machine. I suspect that they flew some Block 1s during some of the earlier Apollos, possibly Apollo 8. But one of the problems they had was that the requirements of the software kept getting more complex, and so they realised in 63 or 4 that the Block 1 machine wasn't going to cut it, and so they had to redo a lot of things for the Block 2. So it did fly some of the early missions, but I don't know exactly which. Good question.
In
Yes.
the descent programs, you had P63.
Yeah.
One other slight question. Was that in the first picture, all that stack of books, was that the program for the landing?
This is actually that picture. That picture. Yeah. So this is. So I've often wondered about this picture, and 2 months ago I thought I must finally research it. I read an interview with Margaret Hamilton. They basically came into the office, they said, we'd like a picture of you, and they grabbed any copy of the source code they could. So this is the source code, but it's probably more than one copy. I would imagine Lumini would fit into one of those binders, but I'm not completely sure.
And P65?
So, yes. Everybody asked about P65. So, in principle, the lunar module could land itself on the moon, and that was the role of P65. P65 was the automatic last bit of the descent. One of the really interesting things about the whole computers in Apollo thing was there was some tension between the astronauts and the engineers and mathematicians. The astronauts wanted to be able to fly the ship manually all the way down. The engineers wanted the whole thing to be completely automated. And the compromise was what I displayed on the screen. It turns out that humans are not very good at doing the orbital mechanics intuitively. So the computer is better at flying most of the descent, but then the compromise was that the astronauts would do the last bit. So P65 in theory could get you down to the ground automatically, but the astronauts always took over and switched to P66, which was just let me do it, please.
Yeah, thanks. You mentioned about the person with the development, the techniques that they use to develop this. So how would it, obviously I work in the world of safety critical software nowadays, so I presume this would either at the time or at least in nowadays thinking would be regarded as sort of safety critical. I don't know whether it would or not. You can maybe answer that. And then how would the sort of techniques they use to develop it in terms of like the development models and life cycles that they use compare with how you develop safety critical software today?
My career is based on soft real-time systems, non-safety critical systems. I don't know a huge amount about safety critical software, so I'd be interested in talking to you afterwards to get your views on it. However, I think this was definitely a hard real-time system and pretty safety critical. You would be a better judge of whether the techniques I talked about would apply today. Actually, in broad terms, would you agree or would you disagree?
And then I'm talking, I think you've got the various life, like the V-shaped model and that sort of thing, where you have rigorous testing at the end and sort of reviews and you specify requirements and design it and that sort of code it and that sort of stuff.
So one of Margaret Hamilton's contributions to the project was turning the software development process into a sort of engineering process and starting to put some of those processes that you've been talking about. Because before then it was much more of a sort of Wild West, less controlled environment for writing programs. So she recognised that this really had to be described as an engineering discipline, and a lot of people laughed in her face when she said that, but she did get results. So I think that the Apollo project, among others, was the start of these rigorous processes, but clearly they've been evolved over time.
Hey,
Alan.
The answer might be the same as the last one, but you mentioned at the start all these limitations the computer had. Specifically, I'm thinking like RAM.
Yeah.
The idea of writing a program now with 2,000 words of RAM at your disposal is kind of terrifying. So how did the programmers ensure that they kind of weren't violating those restrictions? And just more in general, like how did they do rigorous testing to make sure that the program, like all parts through the program were safe?
Yeah. The set of trade-offs they made when writing the software was a bit different compared to modern day. So, for example, in order to have enough space for all of the variables, if you remember I said there was room for 2,000 variables in RAM, they had to reuse the same memory location for different variables, and they would sort of prove to themselves that you'd never need both uses of the memory location at the same time. Nowadays, we'd be like, that's completely crazy. Just put more RAM in the system and don't take the risk of reusing the same bit of RAM. But back then, they had to do various things like that in order to make everything fit. On the flip side, I think it was quite a small and close-knit team of software engineers. They were doing lots of talking to each other, and often in software, the trick is for all your engineers to be talking to each other so that everyone's on the same page. So I think by really keeping it close-knit, they made sure that even though they were making compromises, the system would still fit the constraints.
Question?
Yes.
Sheridan Williams, I'm one of the volunteers here. I was 21 when the Apollo 11 landed on the moon.
I'm very envious.
And I actually saw Apollo 17 take off as well. Went to see that.
I'm doubly envious.
Obviously, I was incredibly interested in the whole thing, especially as my degree's in computer science as well. But when I met someone from NASA, probably a few years after 1969, they just gave me the simple answer that what went wrong was because they forgot to turn the docking radar off. Was it not just that simple?
So this is all this. So yes, you were saying that the issue was that they forgot to turn the radar off, and this has always bugged me because I've thought that there's. if you look at all of the things, all of the planning that went into Apollo, I cannot imagine a situation where an astronaut would have deliberately left the radar switched on when it should have been switched off. That's never made sense to me, and I've never been happy with that explanation. So my take on it is that there was this rare hardware bug, that was definitely found. They definitely figured that hardware bug out. So that was definitely a thing. And the workaround was to add an item to the checklist saying, make sure this radar is switched off. So my take on it is that it was a workaround to get around this hardware bug, rather than the actual cause. 99 times out of 100, they could have left the radar switched on, which they probably did during training, and there would never have been a problem because the hardware bug would not be triggered.
I wonder whether it's because you need to turn it on again when you want to dock, so therefore, rather than turn it off, it shouldn't stay with itself.
It's a difficult story to tell accurately. It's a difficult thing to get to the bottom of because there are conflicting sources of information. But I cannot fathom a world where an astronaut would have just forgotten to turn the radar off and that's the end of the story. That doesn't make sense to me.
Just one further observation on the constraints. I think I wrote my first bit of code in about 1967, we were used to the fact that we had very small memory in the first place. So the whole piece about fitting everything in some senses, was less of a challenge than it might look at from today's perspective, because we certainly couldn't do what you described, which was we'll just stick some more RAM in. So
yes, that's a really good point. We've almost forgotten how to write, or in some sense we're unable to write software. Yeah, I could not write a Hello World that took less than 100 kilobytes.
I was just going to go back to the radar issue, and you were saying that the one of the points was the telemetry.
Yes.
So could Houston see that this information coming in, and so could they debug the problem from the ground, or were they unaware that information was overloading the system?
That's a good question. My belief, but without any evidence, is that Houston couldn't see that this was happening. And the reason why is because the way that the radar feeds information to the computer is by pausing the computer, so stopping the computer running very quickly, giving the I can't see anything data to the computer, and then starting the computer again. It was a very weird way of doing I/O, and because it basically paused the computer's clock, from the computer's point of view, it was like the computer had been cryogenically frozen and then defrosted. The computer woke up again and had no idea it had been paused. Okay. So because the I/O was so low level and so weird, I don't think Houston would have known.
And if they'd chosen to do a P65 landing,
yeah,
and do it completely through the computer, would it have worked, or would it have stayed overloaded?
So the question was, if they did a P65, would it have worked? I don't know. Although, actually, if they'd done a P65, they'd have landed in a boulder field. So, because, and that's the other complicated bit of the story. People conflate the computer issues with Armstrong not landing in a boulder field, and those are two completely different things that often get conflated together.
Do you know how many actual physical instances of the computer there were? How many did they build?
I should know that number. There was obviously 2 for each mission to the moon, one of which came back. I think it's like, in total, even test units, it's the low hundreds, 100, 200. Most of them, tragically, got melted down and scrapped. So nowadays they are incredibly rare. Yeah.
Why is the thing called poodoo?
You are my favourite person. So, I love it when people ask the questions you tell them to ask them to ask. So let me just get a picture of the disky. So we can see on the disky, the top number is the program number, okay? And you know, like on your computer, if you turn on your computer, you might have programs running, but if nothing's running, it's just like the desktop. And the equivalent on the diski was something called program 0. And that would just mean the computer isn't really doing anything. And that was called poo, because it was like program 0. So they nicknamed it poo. And so when the computer did that kind of restart, it closed down all the programs, so it closed down all the apps, and what was left was just the desktop, poo. So that was called a poo-do. So it's because they nicknamed the idle state poo for program 0. Can I also just say, no one's ever asked me that question, even though I've said ask me the question. So that's a great shout. I love it.
I'm assuming they fixed it for Apollo 12, the hardware bug.
So for Apollo 12, the workaround was make sure the radar switched off.
Oh, okay. Fair enough. And also, did they actually know about sort of cosmic ray hits during computers? Because even though they were actually flying through a time when the sun was very active, so that would actually keep a lot of the galactic cosmic rays away. But I just wondered if they knew about them.
The computer was definitely engineered to be sort of radiation hardened, and it used parity checking. So whenever it read numbers from memory, it would sort of check to see sort of have these been affected by external radiation. And I think that the hope was that those parity checks and the radiation hardening would be good enough. And if a parity error occurred, the computer would do a restart.
I was going to say that's core memory, isn't it? Which is naturally resistant to electromagnetic interference.
Yes, interestingly, the parity sort of calculation permeated through a lot of the digital circuits. So I wonder whether they were also trying to protect the actual digital logic from being flipped as well. But I don't know that for certain. James?
So a question I have, you mentioned that a common fallacy is that people assume that it's sort of less powerful than the calculator in your pocket, was
Yes.
the terminology you used. Do you want to sort of give your version of what's actually true? Like sort of what, in modern terms, what is the relative power? What can we compare it to if the calculator example is so far off?
The problem is you can't really compare it to any other machine because it had such a special purpose. It was made for just one thing. You'd struggle to find another machine with that amount of I/O, for example. And my point was more that saying using the clock speed of the computer as a way of comparing its power is meaningless because the real power of the computer comes from the ingenuity that was used to make it special for the actual mission. So it's sort of like apples and oranges. Yes?
Going back to number of units built, was there any redundancy built into the actual kit that was on board?
There was only one computer, so that wasn't redundant. I'm trying to remember if there was more than one IMU. There were certainly things that weren't redundant, and there was only one computer. They could only afford one computer. But if during the lunar descent or any other stage they wanted to abort, then a separate, much smaller computer would take over. And during the landing, one of Buzz's jobs was to manually read numbers from the diski and type it into the spare computer. But the spare computer was a lot simpler. All it could do was do the guillotine and then sort of take you away from the moon, and then you'd sort of fix everything else later. Any other questions?
I'm just wondering, during development, did they have a software emulation or something of this back on the MIT people, or
Yes.
were they working on hardware?
They had both.
But presumably that was really quite difficult because, as you said, the hardware is so intimately tied to the inputs and outputs, and the real-time behaviour must have been very different.
Yes.
And
I can say more. I wasn't sure if you had more questions.
Is that going to tell you anything about how we do things today?
So, one of the lovely things about this computer is there are hundreds of thousands of pages of documentation and test logs and all sorts of things. So it's a real treasure trove. One of the things I found are huge numbers of pages of the results of doing simulations. So they would simulate running the computer, landing on the moon. So they clearly had the capability to simulate things like the IMU in a sophisticated way to test the software. I would give my right arm for a copy of that simulation software, but so far, to my knowledge, no one's found it. But my understanding is they did do extremely sophisticated simulations. And your other question was, how does that tie into today?
So, for example, we do something similar to Cisco.
Yes, we do. We would run software simulations and hardware simulations. Yeah. I would say that the level of testing that they did for the software is comparable to the testing you would do for, say, an aeroplane software today. Like, it was very well tested. Great.
Anyone else? Or Excellent. Well, once again, I'd like to thank Robert for an absolutely fascinating talk.
And could I say thank you very much for coming. It's a real pleasure to be able to talk about something that I'm really interested in to a group of people who look interested. It's absolutely